Stress is defined as force per unit area. In mechanics, there are mainly two types of stresses. The first one is the normal stress. The normal stress is perpendicular to the surface, and it is represented by Greek letter sigma. The shear stress is tangential or parallel to the surface, and it is represented by Greek letter tau. We analyze the stresses acting at a point within a body by using stress elements. What is a stress element? A stress element represents the stresses at a particular point within a body. It can be a three-dimensional stress element or a two-dimensional one, as presented in these figures. We use the three-dimensional stress elements in order to analyze the general state of stress of a particular point, and the two-dimensionals are used in order to analyze the plane state of stress of a particular point. Plane stress occurs when the stresses on one surface are equal to zero. The shear stress is expressed in terms of two subscripts. The first subscript indicates the direction of the surface normal, and the second subscript indicates the direction of the shear stress. And as I indicated before, a particle or a point is represented by a cube with infinitesimal size, and as presented, we use these unit cubic elements. And we all know that a cube has 6 surfaces: top, bottom, front, back, left, and right. Therefore, on each surface, there's a normal stress sigma that is perpendicular or normal to it, and also two shear stress components, tau, that are tangential to it. And we call this the general state of stress of a particle. The normal stress can be tensile or compressive. The tensile stress tends to pull the surface out. However, the compressive stress tends to push the surface in. The compressive stresses are represented by a negative quantity or negative sign, and the tensile stresses are represented by a positive quantity or positive sign. Please recall from the statics course. When we apply the equilibrium conditions, the normal stresses along the same directions must be in pairs with equal in magnitude and opposite in directions. And similarly, again, based on the equilibrium conditions, the shear stresses within the same plane must also have the same magnitude, and two adjacent shear stresses must be either towards each other or away from each other. And in this example, this plane is the YZ plane. In other words, they should be directed in a non-continuous fashion as presented in this figure. And this property is known as the complementary property of the shear stress. Now we will analyze the normal stress under axial loading condition. Normal stress is the intensity of the force acting normal to cross-sectional area. Let's consider a two-force member under axial loading as presented in this figure. In this figure, we have a rectangular bar which is subjected to axial loading, and this force is represented by P. We know that the normal stress in that member can be obtained by finding the ratio of P over A. However, the value of sigma obtained from this equation represents the average stress over the section rather than the stress at a specific point, Q of the section. Let's consider a small area delta A surrounding this point Q, and a force of delta F is exerted on delta A. When this delta A approaches zero, this area becomes a point, and the normal stress at point Q is defined as delta F over delta A. As I indicated before, the stress sigma at point Q varies across the section, and it differs from the average stress value. However, this variation is small in any section away from the points of the application of the loads. As a result, it is assumed that the normal stress distribution and axial loaded part is uniform, with the exception of the immediate vicinity of the points of application of the loads. As a result, we can conclude that an approximation using the average normal stress is generally sufficient, and we can idealize the uniform distribution of the normal stress over the cross-section. This means that we assume that the normal stress is the same everywhere on this cross-section. The integration of the normal stress over the area equals to the normal force. Torsion is a moment that twists or deforms a member along its longitudinal axis. Torsion is the twisting of an object due to an applied torque. And in order to determine the direction of the applied torque, we use the right-hand rule. Please recall that torsion is a vector quantity, therefore it is expressed in terms of direction and also the magnitude. In order to find the direction of the applied torque, we curl our fingers in the direction of the rotation, and our right thumb shows the direction of the applied torque. And why torsion is important actually? What is the importance of torsion? Why should we study torsion? Because many machine parts are loaded in torsion in engineering, either to transmit power, like a drive shaft or axle shaft in a vehicle, or to support some dynamic load, such as a torsion coil spring or a torsion bar. Many power transmission parts are typically circular solid shafts or circular hollow shafts because these shapes are easy to manufacture and balance, and the outermost material carries most of the stress. The torsional deformation is encountered in many engineering structures such as helicopter blades, robot arms, flexible space structures, and wind turbines. The type of stress encountered in torsion is shear stress, and shear stress tau controls the design of torsion members. Why is the type of stress is shear stress in torsion? In order to understand this, you can think of a round shaft as a series of discs glued together on their faces. If you twist the shaft with a torque of T, the glue will be loaded in shear because the load is parallel to the face of each disc. And there are mainly two basic formulas, two fundamental equations when we study torsion. You learned these equations in solid mechanics. The first one is used to calculate the angle of twist. This is the first equation, which is phi or theta, depending on the letter that you use, depending on the Greek letter that you use. You can use either theta or phi. Let's assume that we use theta in order to calculate the angle of twist. We have a circular shaft, which is subjected to an external torque. Naturally, if we apply this torque, this circular shaft will experience some three-dimensional twisting deformation, and we can calculate this theta, the angle of twist experienced by this circular shaft, by using the first equation. Theta equals TL over GJ. Theta is the angle of twist, T is the applied torque, L is the length of the circular shaft, G is the shear modulus, or the modulus of rigidity of the material, because naturally this shaft is made of a material, and J represents the polar moment of inertia. The second basic equation or formula when we study the torsion is related to the shear stress tau, and this is known as torsion formula. We can use this formula in order to calculate the shear stress at an arbitrary radial position ρ. Tau is equal to T rho over J. Tau is the shear stress at this particular radial position ρ. T is the applied torque or the torsional loading. Rho is this radial position. J is the polar moment of inertia. And we also know that the maximum shear stress occurs at the surface of this circular shaft, and it is equal to TR over J. R is the radius of this circular shaft. Both of these equations are known as torsion formula, and they are frequently used in order to analyze the torsional deformation and the shear stress of circular shafts which are subjected to an external torque. If a closed thin-walled tube is subjected to an external torque, we can calculate the shear stress flowing through this tube and also the angle of twist by using these formulas. A thin-walled tube is a one for which its thickness is much smaller than its radius, and the product of shear stress and its thickness is constant. Tau times T is constant. Please note that it is not exactly circular. This one is showing more of an elliptical shape. We can basically sum the moments and relate the shear stress to the total torque by integrating, and at the end it will turn out that we were integrating this quantity right here. We end up getting an area all the way around. And if you would like to calculate the shear stress tau flowing around this tube, we use this formula here. Tau is equal to capital T divided by 2am small t. The capital T is naturally representing the applied torque. Am is the area enclosed by the section median line. And when we would like to calculate the angle of twist experienced by this closed thin-walled tube, we use the following formula here. Theta is equal to TLM over 4G AM squared small t. Here, G represents the shear modulus, as you know. LM represents the length of the section median line. When a beam is subjected to a bending moment, there will be some bending stress develop on the cross-sectional area of this beam. For example, here we have a rectangular beam, a rectangular prismatic beam, which is subjected to an external bending moment. And in this figure, we see the distribution of the bending stress across the cross-sectional area of this beam. And please recall that the bending stress is actually a normal stress, and due to this external bending moment, the normal stress sigma x is developed across the cross-sectional area of this beam. The upper part of this beam experiences compressive stress, while the bottom part of this beam experiences tensile stress. We use a negative sign in order to indicate the compressive stress, and the tensile stresses are represented by positive sign. Sigma x is equal to negative my over I. So this is our flexure formula, which is used to calculate the bending stress, which is actually a normal stress, developed across the cross-sectional area of this beam due to this bending moment. M is the external bending moment. Y is the distance between the point of interest and the neutral axis, and I is the moment of inertia of this cross-sectional area. And we put a negative sign here. When Y is positive, the stress is compressive. When Y is negative, the stress is tensile, because negative is positive. And we also know that the moment of inertia is actually the integral of y squared dA. The maximum normal stress occurs on the surface of this beam, or at the extremes edges of this beam, and it is equal to mc over I. C is the maximum distance from the neutral axis of this beam between the edge of the beam and the neutral axis. Instead of using the moment of inertia, we can also use and substitute the section modulus. The section modulus is also a geometrical property, just like moment of inertia, and the section modulus D is equal to I over C. Let's assume that we have a cantilevered beam. One end is fixed, and this beam structure has an arbitrary cross-sectional area, and it is subjected to a transverse force F. We can analyze the internal shear force and bending moment in this beam and sketch the internal shear force diagram and the bending moment diagram as presented here. For this purpose, first let's determine the support reactions exerted by the fixed support. We have the reaction force F and the bending moment FL. These are exerted by the fixed support, as we know. And then we analyze a small segment at an arbitrary position x, and this small segment has a thickness of dx as presented in this figure. We have already learned how to apply the Fletcher formula. For this reason, we can determine the normal stress distribution on both left and right side of this small segment. The bending stress distribution is shown here in both three-dimensional view and also in profile view. As you can see, the bending stress distribution is different on two sides of this small segment because the internal bending moment changes with x. When I integrate this part of the bending stress here, I obtain a force of Fx, and when I integrate this part of the bending stress here, I obtain a force with the same magnitude but opposite in direction, and these two forces cancel each other out in magnitude. However, they create a pure couple moment that should equal to the bending moment mx at this location. And similarly, when I integrate this part of the bending stress here, I obtain a force of Fx plus dx, and when I integrate this part of the bending stress here, I obtain another force with the same magnitude, however, in opposite direction. These two forces cancel each other out in magnitude. Therefore, they create a pure couple moment that equals to the bending moment at this location, and the resultant force along the x direction is 0. However, what would happen if I would section this top segment horizontally like this and only analyze the top segment? In this case, the remaining forces on the two sides of this segment would be no longer equal to each other. Therefore, in order to achieve the equilibrium, an extra force must develop here at the bottom of this segment, corresponding to shear stress here at the bottom. When we assume this shear stress follows a uniform distribution here, this delta F would be equal to tau times the area of this bottom section, which is equal to T dx. Therefore, delta F would be equal to tau times T dx. Please note that this T represents the width of this bottom section and dx represents its thickness. Then we can write the force equilibrium equation along the x direction as presented here, and sigma represents the normal stress caused by the bending moment at any given position y, and it can be determined by applying the Fletcher formula. Then we substitute this normal stress, which is obtained by applying the Fletcher formula, into this equation, into the force equilibrium equation. Please note that our main objective is to determine this shear stress tau. This is our main objective. Yes, substitute this sigma into this equation and rearrange the equation as presented here. I would like to remind you that this T represents the width of this top segment and I comes from the Fletcher formula, and it represents the moment of inertia of this entire cross-sectional area. And please recall that the derivative of the bending moment, when we rearrange this equation, we obtain here dm over dx. Derivative of the bending moment is actually the shear force. Please pay attention to this integration term here. We can use this integration term in order to determine the central position of this top shadowed area, which is presented in this figure. This integration term here is simply equal to y bar prime times a prime, and it is called static moment of area. I would like to underline that this y bar prime represents the central position of this top segment, this shadowed area is presented in this figure, and a prime represents the area of this shadowed portion, which is the top segment. And the static moment of area is also called the first moment with respect to the given axis, which is the z-axis in our case. As a final step, when we replace this integration term by the static moment of area Q, we obtain the final shear formula. This is used in order to calculate the shear stress caused by a shear force V. Tau is equal to VQ over RT. Tau represents the shear stress, V represents the shear force causing this shear stress, Q represents the static moment of area, which is also known as first moment with respect to the given axis, which is the z-axis. I represents the moment of inertia, and T represents the width of the segment. Now, let's focus on a small differential element here, and let's zoom on this element. According to our previous analysis, we know that a shear stress develops here at the bottom of this element, and the magnitude can be determined by applying the shear formula VQ over IT. However, we have also learned about the complementary property of the shear stress. If a shear stress develops on this side, on the bottom side of this element, we know that it must also develop on the other three sides as well with the same magnitude. When we assume that the shear stress is uniformly distributed along the z-axis, and when we apply the method of sections multiple times and also apply the shear formula multiple times, we can determine the shear stress distribution across the entire cross-sectional area as presented here. And the integration of the shear stress over the entire cross-sectional area should be equal to the internal shear force V at this location. Let's look at this example. In this problem, we are required to determine the shear stress distribution for this rectangular cross-sectional area. Let me read the problem statement. For the rectangular cross-sectional area subjected to internal shear force V, determine the shear stress distribution as a function of Y. If you recall, during our previous lectures, we learned how to determine the average shear stress value. The average shear stress for this rectangular cross-sectional area would be equal to V over A. V is the applied shear force and A is the cross-sectional area. Please note that this V is parallel and tangential to this cross-sectional area, and the area is BH because we have a rectangular cross-section. However, in the reality, we will use the shear formula because it is actually not uniformly distributed. The shear stress in the reality is not uniformly distributed, and it is a more complicated distribution across the cross-sectional area of this rectangle. And we can determine the shear stress by using the shear formula VQ over IT. And I is the moment of inertia, and we know that the moment of inertia of a rectangular cross-sectional area is simply equal to 1 over 12 times B times H to the third power. Then we choose an arbitrary location Y for our analysis and pick the top segment. The centroidal location of this shaded area is in the middle with a distance of Y bar prime from the z-axis. And we can determine that through our knowledge of geometry. We also need the area of this shadowed portion, and we can determine it by using this equation here. Q represents the static moment of area, and we know that it is equal to Y bar prime times A prime. Please recognize that T represents the thickness of this section, and it is simply equal to B. And as the last step, we substitute all of them into the shear formula. Ta equals VQ over IT represents the shear formula. And when we substitute all of these variables into this shear formula, we obtain this last equation here. Ta is equal to 6V over B times H to the third power, and we have this expression inside the bracket. Please note that the shear stress here is a function of Y. So it's a quadratic function, it's not linear. This indicates that the graph of the shear stress should be a parabola. And we can plot this shear stress distribution as a function of Y as presented in this figure. Please note that unlike the bending stress distribution, shear stress doesn't follow a linear distribution, but it has a parabolic shape. At the two edges, the shear stress is 0, and at the centroidal location of this cross-section where Y is equal to 0, we have the maximum value of the shear stress, which is equal to 1.5 times average shear stress tau. We can also integrate the shear stress tau across the entire cross-sectional area. In this case, it is equal to V, the internal shear force at this location. Now let's analyze the topic of stress transformation. What is the objective of stress transformation? The stress transformation is performed in order to obtain the normal and shear stresses acting on a particular plane or on an inclined plane. Because we might be interested in the stresses acting on a weld or on an adjusted joint, or probably we might need to determine the largest normal stress for any orientation of the stress element in order to analyze how and when the material will experience failure. For example, here we have two different structures. The first one is wood. It's a wood structure made of two different wood parts, and these two wood parts are glued together. And we might be interested in the stresses acting along this glue line. For example, probably we need to determine the normal stress and the shear stress along this glue line in order to make sure that the structure will not experience failure. And in the second example, we have a metal plate. This metal plate is made of two different other metal parts which are welded together. And again, we might be interested in the stresses acting along this welding line, because we must make sure that the stresses developed along the welding line will not exceed the maximum allowable stress, so that this metal structure will not experience failure or fracture. Stress transformation equations are determined by considering an arbitrary prismatic wedge element as presented in these figures. Figure A represents the geometry of this wedge element, and figure B represents the free body diagram. It illustrates all of the forces and stresses acting on the three faces of this prismatic wedge element. The stress components sigma x prime, sigma y prime, and tau x prime y prime associated with this element are determined after this element has been rotated through an angle of theta about the z-axis. And now we will express these rotated stress components, namely sigma x prime, sigma y prime, and tau x prime y prime, in terms of original stress components sigma x, sigma y, tau xy, and also the rotation angle theta. For this purpose, we will write the force equilibrium equations acting along the x direction, acting along the x prime direction and y prime direction. Since this prismatic wedge element is in equilibrium, the sum of the forces along the x prime direction are equal to 0, is equal to 0. And again, the sum of the forces along the y prime direction is also equal to 0. Let's first write our force equilibrium equation along the x prime axis. The first force is the one which is produced by sigma x prime. Sigma x prime is the normal stress which is perpendicular to the oblique face of this prismatic wedge element. The area of the oblique face of this prismatic wedge element is represented by delta A. And sigma x prime times delta A represents the normal force acting on the oblique face of this prismatic wedge element. But we have also other forces acting along the negative x prime direction when you look at the free body diagram. Please look at the free body diagram and try to understand it. There are also forces along the negative x prime direction, and these forces are produced by sigma x, tau xy, sigma y, and tau xy, the other component, because tau xy is producing two forces. Here, as you can see, if you look at the first component is along the negative y direction, and the other component of the force, which is produced by tau xy, is along the negative x direction. And by multiplying them by sine theta and cosine theta, we are finding the components of the forces which are produced by tau xy. Sigma y is also a force component, also is producing a force component acting along the negative x prime direction, and this is equal to sigma y times delta A sine theta, which is the force produced by sigma y along the negative y direction, and when we multiply it by sine theta, we find its component along the negative x prime direction. And after that, we establish our second equilibrium equation along the y prime axis. Sigma fy prime is equal to 0 because this prismatic wedge element is in equilibrium. Again, we find the sum of the forces acting along the y prime direction by following a similar manner. And this is our second equilibrium equation. by solving these two equilibrium equations, we can obtain the sigma x prime and tau x prime y prime, and these equations are known as stress transformation equations. By using these equations, we express the normal stresses along the x prime and y prime direction in terms of the normal stresses along the original coordinate system, namely in terms of sigma x, sigma y, and also tau xy. And we can also express the rotated shear stress tau x prime y prime in terms of sigma x, sigma y, and tau xy. So in general, we can conclude that these sigma x prime, sigma y prime, tau x prime, y prime are the rotated stress components, and they can be expressed in terms of the original stress components sigma x, sigma y, and tau xy by using these equations. These equations are known as stress transformation equations since they transform the original sigma x, sigma y, and tau xy stresses. And yes, these equations are known as stress transformation equations. In summary, we can use these stress transformation equations to calculate the new state of stress when an element has rotated from its original orientation by an angle of theta. If you look at these three equations, you will notice that theta is actually the only independent variable here. Therefore, these three equations can be considered as a function of theta. Please recall from math, critical points always correspond to either minimum or maximum value of a function. And for these three functions, we also want to find their critical points in order to determine the maximum normal stress and maximum shear stress. In mechanics, the maximum and minimum normal stresses are known as principal stresses. For the first equation, if you want to find its critical points, which represent the principal stresses, namely maximum and minimum normal stresses, we take its derivative with respect to theta and set it to 0. From this equation, we can solve for theta in terms of tangent to theta. Since sigma x, sigma y, and tau xy are all known, we can evaluate theta, and we can give theta a special name such as theta v, theta p. Since it corresponds to the principal stresses, we can use this p letter. And please recall that the principal stresses are actually minimum and maximum normal stresses. Similarly, by following a similar strategy, we can determine the maximum in-plane shear stress, which is represented by tau x prime y prime. In this case, we take the derivative of this equation with respect to theta, set it equal to 0, and we find the orientation of the plane where the maximum in-plane shear stress occurs. Theta p represents the orientation of the principal planes where the maximum and minimum normal stresses occur, and theta s represents the orientation of the plane where the maximum in-plane shear stress occurs. Yes, when we substitute these two theta p values into our stress transformation equation, we find the minimum and maximum stress values, namely the principal stresses. These principal stresses can be represented by the subscript of 1 and 2. Sigma 1 represents the maximum normal stress, sigma 2 represents the minimum normal stress, and they can be determined by using these following equations. Sigma 1, 2 is equal to sigma x plus sigma y over 2 plus minus the square root of sigma x minus sigma y over 2 squared plus tau xy squared. As you can see, we can determine the maximum and minimum normal stresses, namely principal stresses, as a function of sigma x, sigma y, tau xy. And theta p represents the orientation of the planes where we observe these maximum and minimum normal stresses. In other words, theta p represents the orientation of the principal planes. And I would like to underline that on these principal planes, the shear stress is equal to 0. If you substitute this theta p value into our stress transformation equation for tau x prime y prime, you will observe that the shear stress value corresponding to maximum and minimum normal stresses is equal to 0. And please also note that these equations are actually the parametric equations of a circle. We can apply a similar analysis to the shear stress function. Again, we want to find the critical shear stress values. For this purpose, we take the derivative of this shear stress function with respect to theta, set it to 0, and solve for theta in terms of tangent to theta. The subscript S here represents the shear stress. As presented in this figure, for an element with a given plane state of stress, its maximum in plane shear stress can be determined by orienting this element by an angle of theta S1 or theta S2, and difference between these two angles is 90 degrees. These two angles can be evaluated by using this equation, this tangent to theta S equation. And if you would like to know the normal stress on four sides of this stress element, please note that the normal stress is the same on all four sides of this element, and the normal stress equal to the average normal stress of sigma x and sigma y. By substituting this theta s value, the corresponding solution value, into the stress transformation equation related to the normal stress, you can realize that where we have the maximum in plane shear stress, we have the average value of the normal stress on all of these four sides of this stress element. In either orientation, the maximum shear stress has the same absolute value. It is either positive or negative depending on the orientation. Please compare this tangent 2 theta s formula to the tangent 2 theta p formula that we have analyzed on the previous slides, and you will realize that tangent 2 theta s formula is actually the negative inverse of tangent 2 theta p formula. This means that 2 theta s and 2 theta p are 90 degrees away from each other, therefore theta s is 45 degrees away from theta p. Please note that the previous equations represent the parametric equations of a circle. We can also use a graphical method to visualize and analyze the stress state of a particular point within a body, and this graphical method is known as Mohr circle. Mohr circle method allows you to determine the normal and shear stress components for different orientations of the stress element graphically. And instead of using these stress transformation equations, we can just construct a Mohr circle so that we can visualize and analyze the stress state at a single point within a structure in terms of by using stress elements. The horizontal axis on Mohr circle represents the normal stress sigma, and the vertical axis tau represents the shear stress, as we know. And when we construct the Mohr circle, we first locate the center of the circle, C, which corresponds to the sigma average, sigma x plus sigma y over average, sigma x plus sigma y over 2. So the sigma y plus sigma x over 2 is the average stress, and it corresponds to the center of this Mohr circle. After that, we plot an x point on this circle, and the coordinates of this x point corresponds to the stresses acting on the x phase of our original stress element. When you look at the figure A, you will notice, so the coordinates of this point x corresponds to the stresses acting on the x phase of this stress element. And after that, we plot another point, the y point on this circle, and the coordinates of the y point correspond to the stresses acting on the y phase of this stress element. Again, I would like to repeat, this is important. The coordinates of the x point correspond to the stresses acting on the x phase, and the coordinates of the y point correspond to the stresses acting on the y face of our original stress element. Now, we draw a line connecting these x and y points, and the half of this line will give us the radius of this circle, isn't it? The half length of this line will give us the radius of this circle. And if we use our knowledge from trigonometry and geometry, we know that the r is equal to sigma x minus sigma y over 2 squared plus tau xy squared. Then we take the square root. Again, the radius of this circle is equal to the square root of sigma x minus sigma y over 2 squared plus tau xy squared. So we can find the radius of this circle geometrically, and also we can use this equation. This represents the radius of this small circle. And when you look at this figure, you can also realize that the average stress plus R represents the maximum normal stress, and the average stress minus R corresponds to the minimum normal stress. And please recall that the maximum and minimum normal stresses are known as principal stresses, which means that the principal stress sigma max and sigma mean are equal to sigma average plus minus R. And you can find the orientation of these principal planes either by using your knowledge from trigonometry. We can use this Morse circle and we can determine theta p, or we can just use this equation that we have obtained on the previous slides. Tangent to theta p is equal to 2 tau xy over sigma x minus sigma y. And each of these theta p corresponds to the plane of principal stresses. So it represents the principal planes. I would like to underline that these 2 points are important. The points on the Morse circle represent the stresses on an element, and any angle we get on the Morse circle should be divided by 2 to get the actual rotational angle.